In this video, we're going to look at an example that is convergent conditionally. So we're being asked to determine whether this alternating series, the sum from 1 to infinity, negative 1 to the n, times n over the square root of n cubed plus 2, is absolutely convergent, conditionally convergent, or divergent. So in order to have something that's conditionally convergent, we need to have some negative terms. And certainly here we have some negative terms in here. Some negative terms and some positive terms. We need something that's usually alternating, but kind of alternating like, I suppose you could say. All right, so if we're going to check to see that this has conditional convergence, but is not absolutely convergent, well, the first thing we're going to do is check absolute convergence. We're going to look at the series formed by taking the absolute value of the terms and seeing what happens. Because if it's absolutely convergent, then the original series converges and you're done. There's nothing else to do. All right, so first thing we do, take the absolute value of the terms. The only thing that does is knock out this negative 1 to the n and makes this the sum from n equals 1 to infinity of n over square root of n cubed plus 2. This looks like a good candidate to use the limit comparison test on. The top is n to the first power. The bottom is, well, not is, but looks like n to the 3/2 power. So we'll compare it to the series of n over n to the 3/2, which is 1 over n to the 1/2. And notice that this is a p series. P series are great things to compare other series to if you can, because we can tell whether or not a p series converges or diverges simply by looking at the power on the n and the denominator. All right, so for the limited comparison test to apply, we need both series having all positive terms, which we certainly have, and we look at the limit of the ratio of the two, and as long as that turns out to be a number that's not 0, whatever one series does, the other series does. We've talked about this before. All right. So take the limit here. Remember we got n, or 1 over n to the 1/2 from n over n to the 3/2. So if you imagine this as being n over n to the 3/2, we're going to match the n pieces together and the n to the 3/2 pieces together. The n over n cancel each other out. I can pull the n cubed under the radical. And then certainly as n goes to infinity, the inside here goes to 1, because it's n cubed over n cubed essentially. Square root of 1 is 1, so this limit turns out to be 1, which is certainly not 0. So since the thing we're comparing to, this p series that we're comparing to, diverges, and the way we can tell that it diverges is the power on the n is 1/2 in the denominator, and the 1/2 is less than 1. Since this series diverges, the series without this alternating piece, this should just say this original series here, n over square root of n cubed plus 2. We should not have this negative 1 to the n in here. Sorry about that. That series diverges as well by the limited comparison test. So again, this piece right here should not be in here. So the original series is not absolutely convergent. All right, so what about conditional convergence? Well, conditional convergence is always, for our purposes, will always be determined by the alternating series test. We're not going to be doing problems of conditional convergence unless the original series was alternating to begin with. Strictly alternating, literally positive, then negative, then positive, then negative. We've seen this example before in a previous video, but going through it again, here's the non-alternating part. Take the derivative to show that the function is decreasing. So if I take the derivative using the quotient rule and then simplify, we see that this derivative is negative so long as x is bigger than the cube root of 4. Cube root of 4 is between 1 and 2, so this will be negative as long as x is bigger than or equal to 2, which means that the sequence of terms that we're interested in decreases for n bigger than or equal to 2. Take our limit. It's probably easiest here to just notice that we have n over square root of n cubed, essentially, n to the 3/2, like we talked about for the limit comparison test. Divide top and bottom by n to the 3/2. we get 1 over n to the 1/2 on top, and then a 1 plus, this should be 2 over just a n cubed. When you pull this n cubed into the radical, there shouldn't still be a half there. So this should be 1 plus 2 over n cubed. Sorry about that typo as well. My apologies. The important part is this goes to 0. This also goes to 0. So this whole thing just goes to 0 over 1, which is 0. So the terms are going to 0, the limit, and they're decreasing. So the series, the original series, converges by the alternating series test. That means that since it was not absolutely convergent, it must be conditionally convergent.